Hello, my name is Mohammad Saatialsoruji. Today, I'm going to be presenting my research on resolving deadlocks and livelocks in lifelong multi-agent pathfinding using real-time LaCAM. This research has been completed at Carnegie Mellon University's ARCS lab under the supervision of Professor Jiaoyang Li as part of the RIS program. So, to contextualize the significance of the multi-agent pathfinding or MAPF problem, modern warehouse automation requires the navigation of dozens to even hundreds of robots in a shared environment. To understand the core challenge, let's first define formally the MAPF problem. Imagine our world as a shared grid world, discretized into individual cells and time steps. We have a team of multiple agents where each agent must move from its starting location to its goal location. At every discrete time step, an agent can either wait in place or move up, down, left, or right. The catch is that the joint movement of all robots must remain entirely collision-free. This means that two agents can never occupy the same grid cell at the same time, which is what we call a vertex conflict. And also, two agents cannot swap adjacent positions simultaneously, and this is what we call an edge conflict. Also, there are two problem settings for MAPF. There's what we call one-shot MAPF, where the problem ends once each agent hits its first goal. And then there's the lifelong MAPF setting, which is what this research is tackling. And that is the setting in which once an agent finishes a task, it is immediately assigned a new goal, and this requires continuous real-time planning. Now, the challenge with real-time planners and lifelong MAPF is that many real-time planners struggle from deadlocks and livelocks where two agents trap each other and get stuck, or just repeat an infinite cycle with no progression towards their goals. And this causes the throughput of the system to degrade over time. So the completeness guarantees of offline full horizon planners for one-shot MAPF do not extend to these real-time planners. Now, to put our approach in context, let's look at the existing baselines. First, we have PIBT, or Priority Inheritance with Backtracking. This is an extremely fast planner that generates single-step moves. It works by passing priorities between adjacent agents to resolve local head-on conflicts. But the issue with PIBT is that it is fundamentally incomplete, and in dense environments and narrow corridors, agents can easily lock each other into permanent cycles. So in the image we have in the slide, we see a very clear case where PIBT gets stuck in a deadlock. We have two agents. Um, the higher priority agent occupying cell B2 wants to move to cell A2, which is already occupied by another agent. So according to the PIBT logic, agent 1 will pass its priority to agent 2 to get it to move out the way. But because agent 2 is completely trapped, it will tell agent 1 to pick its second best move, which in this case would be for agent 1 to move in place, and both agents will get stuck and no progress will be made. Now, to fix this issue, LaCAM, or Lazy Constraints Addition Search for MAPF, introduced a complete joint space search. It uses PIBT as a fast subroutine to generate candidate configurations inside a DFS tree. If a state leads to a deadlock or livelock, LaCAM backtracks and applies constraints to force the search to take alternative branches until a full collision-free path to all goals is found. Each node in the LaCAM tree represents the joint state of all agents, and each solid arrow represents a one time step conflict-free transition generated by PIBT. Each dashed arrow represents the backtracking mechanism. LaCAM has provable completeness for one-shot full horizon planning. Now, while LaCAM is powerful, planning full horizon paths offline isn't feasible for real-time execution, and this led to real-time LaCAM. Real-time LaCAM modifies LaCAM such that instead of searching the entire horizon at once, real-time LaCAM runs within a strict per iteration time cutoff. When the time budget expires, agents execute the best available step, and real-time LaCAM dynamically reroutes its search tree at the newly executed physical location. This preserves constraint memory across physical execution steps without having to throw away past search work. So real-time LaCAM is able to achieve real-time execution while still preserving the completeness guarantees we get from full horizon LaCAM. However, a key gap still remains, which is that real-time LaCAM was engineered specifically for one-shot MAPF, where agent goals never change. But in the lifelong setting where agents continuously receive new goals, naive tree rerouting breaks because old search memory no longer aligns with the new target locations. Um, and this is the specific challenge that our proposed framework tries to solve. Now, our approach builds on three key components. The first is task indexed memory. Instead of throwing away search memory when goals change, we index high-level search nodes using both agent spatial positions and individual task completion counters. Additionally, each node maintains two distinct pointers, a mutable search parent that handles dynamic tree rerouting for active exploration, and an immutable history parent that preserves the exact search branch sequence. This allows the system to preserve search memory across physical execution steps while ensuring that goal updates for one agent safely invalidate only its own outdated history without erasing useful context for unaffected agents. Second is our online deadlock detection. To catch deadlocks early, we inspect agents appearing in active PIBT push and block interaction traces. For candidate agents, our detector inspects recent branch ancestors and compares their local vicinity signatures, which tracks the agent's cell, task index, and surrounding neighbors. If an agent repeatedly returns to the same vicinity signature without making progress towards its goal, the system will flag that agent as deadlocked. Third is the local subgroup repair. So once a persistent local cycle is confirmed, the deadlocked agent acts as a seed to form a subgroup or a localized meta agent subgroup with its deadlocked neighbors and blockers. Then a local LaCAM instance will search for an escape path for just those subgroup members on the static map, ignoring outside agents. At each time step, the subgroup's next move is supplied to the global PIBT as fixed member moves, allowing PIBT to plan collision-free actions for all outside agents around them. If an outside agent prevents the coordinated action of the meta agent, we adaptively expand the subgroup to absorb the blocker and then replan. Once any agent in the subgroup reaches its goal, the subgroup will automatically dissolve and the deadlock will be broken. So here this shows the steps of our algorithm. So first, real-time LACAM and PIBT will execute normally and record push and block interactions. Then interacting agents will be checked to see if there's a persistent local cycle. And if an agent is found to be in the same position with the same neighbors and no progress, then we will create the agent subgroup and use a local LACAM instance to plan the subgroup paths to goals. And then um, the subgroup moves will be executed together. And then we will either continue, dissolve, or expand. So we evaluated our algorithm against PIBT across standard benchmarks over extended time steps. In dense grid environments with 200 and 400 agents, PIBT's performance rapidly degrades over time, eventually freezing completely. Our algorithm maintains high stable throughput continuously over all steps. Um, in narrow one-width corridors like the maze map on the bottom left, where agents face head-on deadlocks, PIBT drops permanently to zero throughput, but our algorithm is able to recover the system's throughput. On more open maps, like the one we see on the bottom right, our algorithm performs similar to PIBT with minimal computation time overhead. In terms of theoretical guarantees, our algorithm provides the guarantee that the system throughput will never permanently be zero, so at least one agent will continue to achieve tasks. In conclusion, our method is able to successfully prevent persistent throughput collapse in dense and narrow lifelong MAPF environments. In cases where PIBT fails. For future work, we plan to extend the framework to large rectangular agents where orientation and rotation constraints matter. And we would like to address the frequent deadlocks caused by multi-cell footprints and narrow corridor blockages.